Internet's routing system is notoriously insecure, allowing adversaries to launch attacks that discard traffic, impersonate a service, or perform eavesdropping. Yet a strategic adversary can do so much more damage by launching application-specific routing attacks that attack services with security and privacy concerns of their own, like the Tor anonymity system, certificate authorities, and Bitcoin. So in this talk, I'm going to discuss some of these application-specific routing attacks and also application-specific defenses that can protect against these attacks while we continue the long-term work of securing the Internet's routing infrastructure. But first, just to refresh our memory about BGP, BGP is the glue that holds the disparate parts of the Internet together by allowing an autonomous system to announce an address block that it can reach and allow it to diffuse across the Internet to other parts of the Internet. But unfortunately, it's vulnerable, like many Internet protocols, to attack and misconfiguration, where an autonomous system that is not authorized to announce a particular address block does so and tricks other parts of the Internet to routing to or through that AS. So these attacks can affect availability if the attacker drops the traffic on the floor, or confidentiality if the adversary interposes himself on the path and eavesdrops on the communication. This is, of course, not new information. BGP's had security problems for many years, and there's been lots and lots of work on trying to improve the security of the routing system. But deploying these security solutions is hard and takes place gradually. And so we still see the routing system having a lot of vulnerability, particularly to strategic adversaries that are intentionally introducing attacks. And yet, there are a lot of applications on the Internet that provide important services to users that have security and privacy properties that are important as well. Things like Tor, the onion router, that provides anonymity to users browsing the web, or certificate authorities that give out certificates for SSL, or Bitcoin, the cryptocurrencies. And so these applications are written to treat the network as a dumb pipe, which is natural. This is one of the great benefits of layering, is that we can ignore the underlying network layer when writing higher level applications. But unfortunately, BGP doesn't provide sufficient scaffolding for these applications. And in fact, what we see is that assumptions made in one layer about the layer below can lead to vulnerabilities that can be exploited by an adversary to violate the security and privacy properties these applications assume. But fortunately, these attacks are very targeted, and these applications are very incentivized to deploy security solutions of their own. And so we'll see that although there are powerful attacks that can be launched on these applications from below, there are also natural application-specific defenses that can be deployed to protect against them. But just to set the stage, I'm just going to go through a little bit of background on BGP attacks. Most of this is probably old hat to most of you, but just to get us all on the same page, you can imagine an autonomous system 6 here that's announcing an address block like 1234/16. All the Internet is routing traffic through it. And an adversary on the other end of the net could announce the same prefix, and some fraction of the Internet is going to believe this erroneous route, particularly if its upstream provider doesn't filter it. And so on average, about half of the Internet, the part of the Internet sort of logically closer to the adversary, will be directing traffic through to the adversary rather than to the legitimate destination. And the adversary might drop the traffic on the floor or impersonate the legitimate service. But fortunately, attacks like this are relatively easy to detect because the last hop in the AS path does not match the one that usually introduces this prefix into BGP. So BGP anomaly detection systems or the RPKI would detect these kinds of attacks as they're gradually more and more deployed. So a smarter adversary would perhaps go further and try to evade detection by forging the last hop of the AS path so that it looks like that this AS has a legitimate link to the actual rightful owner of this address block. And so this path being announced into BGP will look legitimate because the last hop matches the expected one. And so it would fool a lot of BGP anomaly systems and early uses of RPKI. Now, in return, some of the ASs in the Internet won't pick this route because it's slightly longer, but the adversary can still attract a certain fraction of traffic that's meant for the legitimate destination to itself. The adversary gets a little smarter. It can more generally sculpt which ASs in the Internet pick its route over the legitimate route to the destination. In particular, BGP path poisoning will allow that. So for example, suppose this adversary doesn't want Autonomous System 3 to route to it. It would rather only attract traffic from Autonomous System 2. Then it could put Autonomous System 3's AS number in the path so that upon receiving this route, Autonomous System 3 would do loop detection and discard the route. so it would not pick that route, let alone propagate it to others. And so this provides a general mechanism, as does the use of BGP communities, for the adversary to determine exactly who's going to pick the route that it gets advertised. And so we're particularly interested here in how a smart adversary might use these kind of mechanisms to fly under the radar screen, to announce bogus routes that won't set off alarms, won't violate our PKI, and yet will only trick a small fraction of the internet, exactly the part that the adversary wants, into routing the wrong way. So in particular, we're interested in attacks that target a particular sender or a set of senders of which you need to fool just one, with limited scope, where our goal is only to have the ASs necessary to deliver the traffic be convinced to route through the adversary. This will limit the visibility of these attacks in the routing system, helping evade detection, and limit the amount of data traffic that follows the hijacked path, limiting the overhead on the adversary to carry that traffic and limiting the detectability of the attack. And we'll note that some of these attacks can take place for a very short period of time and still be effective, again, limiting the overhead for the adversary and minimizing the chance that it gets detected. And so what kind of attack we mean here is, suppose an adversary now in AS4 wants to attract traffic just from autonomous system 1 and doesn't want the rest of the internet to route to it. Then it could do path poisoning to have the autonomous systems adjacent to the path AS1 takes to reach AS4 discard the route due to loop detection, so that the AS1 sends traffic through the adversary, but the other ASs continue routing normally to the correct destination. Now, why would the adversary want to do this? Well, we're going to look at one concrete example related to certificate authorities, where the adversary's goal is to have a particular certificate authority, or any one certificate authority that's most easily attacked, direct traffic to the adversary instead of the legitimate destination. And we're going to do that precisely at the time when the adversary is going to try to get a certificate for a website controlled by the victim. This attack now will have limited scope and last for a limited duration under the control of the adversary, who is the one asking for the certificate. So just to be a little more concrete, if you're trying to get a certificate for a website, you've just set up a new website, you want to be able to run HTTPS, you need to get your certificate signed. And so you'll go to a certificate authority like Let's Encrypt, and you'll say that you would like them to sign your certificate. Now, the certificate authority is going to want to check if you're the legitimate owner. Are you actually in control of the site, the domain that you're asking about? And so it's going to want to verify that. And so it's going to send back a domain control validation request. It's going to say, hey, if you really are in control of this website, go to it right now at this particular URL and put this content there. And I'm going to check moments later. And you have to essentially prove to me that you have enough control of this website to update its contents quickly. And then the result will come back and I'll verify that, yep, you're the legitimate party in charge of this site. I'll sign your certificate and you're on your merry way. And that's how it works normally, but an adversary might choose this precise moment to launch a hijack so that the domain validation request comes to the adversary rather than the legitimate website, where the adversary can now produce the intended response, fooling the certificate authority into giving out a certificate to the wrong party. With the certificate in hand, now the adversary can launch man-in-the-middle attacks on HTTPS traffic destined to that victim domain. So that's the kind of attack we're worried about, where the adversary just needs to fool the certificate authority into routing to the wrong place, and just briefly at a time of the adversary's choosing. So a few years ago, we worked on identifying this attack and then demonstrating it in the wild using the peering testbed at Columbia. So we took an IP prefix that we controlled through that testbed, domain names that we created, and clients that we ran, so that we wouldn't actually affect any real traffic on the internet. And we did this attack where we hijacked ourselves and asked for a web certificate during that narrow window of time. And we did this attack on the 5 main certificate authorities that all do domain control validation, either of HTTP, like I showed a moment ago, or using the email server of the domain. All 5 of these CAs signed our certificate request in less than 2 minutes, and we were good to go with bogus certificates in under 2 minutes. So what should we do about this? This is clearly a vulnerability in a protocol that exists to create security on the internet. And so I want to note also, although I'm going to focus mainly on domain validation requests sent to the websites, you could also imagine hijacks of the DNS server of the domain or the mail server of the domain. And you can also imagine hijacks on the reverse traffic from the legitimate domain to the certificate authority, where the adversary can interpose itself as well. But we'll focus mainly on the case where the adversary is trying to stop the legitimate domain from receiving the validation request so that an erroneous response can be generated. So what can you do about this? Well, one possible application layer defense is pretty simple. And before I get to that, though, I just want to mention one more thing, which is attacking any one certificate authority is already a risk, but there's an additional risk here that there are actually around 100 different certificate authorities, and any one of them can sign a certificate request for a domain. And so an adversary has the option to choose not only the victim, but which certificate authority to try to fool. And so in this picture, certificate authority 1 is relatively close to the victim, and it'd be quite hard for the adversary to be successful in launching a prefix hijack that tricked the CA into routing through the adversary. But there might be a second CA closer to the adversary and further from the victim that's much easier for the adversary to attack. And so a real challenge here is not that, hey, half of the destinations on the internet might be attacked by the adversary, but in fact, almost all of them can be if the right certificate authority is used to launch the attack. So the adversary can control its own position, which victim it's after, and which CA it's going to try to trick, giving the adversary a lot of power in launching attacks like this. So what's a possible defense? Well, a simple idea is that it's possible to fool some of the people some of the time, but not all the people all the time. In particular, it's not hard for an adversary for a brief window of time to fool one vantage point run by a certificate authority. But to fool multiple vantage points distributed across the internet topology across the globe will be much more difficult. The adversary would have to fool all or most of them to get a certificate. And that's essentially what we've done is we've worked with Let's Encrypt to do multi-vantage point domain validation so that a stealthy adversary would have difficulty actually tricking all of these vantage points into routing through the adversary, and particularly have difficulty doing so without being detected. A large-scale attack that is visible to all of these vantage points would also be widely visible and much, much easier to detect. And so about a year ago, Let's Encrypt deployed multi-vantage point domain validation. And what I want to do in the next few minutes is talk a little bit about our experiences working with Let's Encrypt on the deployment and evaluation of their deployment, to look at what's involved in building these application layer defenses. Now, I mean, at a high level, this sounds super easy. Instead of verifying from one vantage point, verify from multiple. But we've got a lot of challenges to address here. We want, of course, security. That's our primary goal. So we want these vantage points to offer diverse perspectives, to make independent routing decisions so that it would be unlikely they'd all be fooled by the same adversary. And that means we also need a quorum policy, a vote, if you will, that really requires most, if not all, of these vantage points to agree before we decide to give a certificate. Yet we want this to be manageable. And in fact, certificate authorities are subject to the CA browser forum that puts pretty strict requirements on where domain control validation can be done. And so we want to be compliant with those requirements. And we also want to run multiple vantage points without introducing a ton of cost and complexity to run those multiple vantage points. We also want to minimize the latency and communication overhead for the many legitimate requests that are made to certificate authorities and avoid rejecting valid requests for certificates, as the vast majority of the requests are expected to be valid. So I'm going to walk through how we handle each of these issues in the deployment that Let's Encrypt has done. So the CA browser forum requires that domain control validation be done from data centers with certain standards for physical security. And they do auditing of those data centers to make sure that they're suitable. So making all the vantage points have to comply with the CA browser forum requirements would be quite onerous. So instead, what we do is have a primary VA, a primary vantage point, that's in a data center compliant with the forum. That's already in place even before Let's Encrypt started working with us. And instead, then add a bunch of remote VAs on top of that existing primary VA that may be running in public cloud networks. And in particular, in the Let's Encrypt deployment, they're using Amazon Web Services. This offers the manageability benefits of using the public cloud in combination with the primary VA being compliant with the browser CA forum. But because of that, we also have to treat the primary VA as special. In other words, we can't grant a certificate if that VA is unable to validate, do domain control validation. So whatever quorum policy we pick has to have the primary VA succeed in validating the request for the domain, and some number of the remote VAs have to succeed as well. So that way we would never give a certificate in a setting where the old solution would have chosen not to, but we may be more strict and not give one sometimes when the old solution would have. So second, now we want to balance the security that we offer against the complexity of running these remote VAs in what might otherwise be many public clouds to get truly independent vantage points on the internet. And fortunately here we find that using a single cloud provider, multiple data centers, but run by the same cloud provider, offers sufficient route diversity. So we don't have to have the complexity of using multiple cloud providers with multiple billing models and multiple ways of instantiating VMs. And so in practice, we can actually have a solution, this is what Let's Encrypt does, that has just one relationship with a single cloud provider. And in particular, with Let's Encrypt, they have their primary VA either in Denver or in Salt Lake City in the US, and remote VAs running in AWS in Oregon, Ohio, and Frankfurt. And we'll come back later to these particular choices and whether more vantage points would be helpful. So next, now the system is relatively easy to manage, but we still have to worry about benign failures, where a legitimate request might be erroneously rejected. And how can we minimize the performance impact to benign users as well as the risk of giving them an error message? So these remote VAs, these remote vantage points, they may respond slowly, which could give latency to valid requests. They may fail to respond for legitimate reasons, some sort of outage, or they may give inconsistent answers. And we'd like to be able to make sure that we're not vulnerable to that happening to legitimate requests. And so to allow a bit of robustness to a single remote VA having a problem, we're going to have a quorum policy where the primary VA has to succeed in validating the domain, and 2 of the 3 VAs must do so. And you can imagine stricter or weaker models here, but the idea of allowing at least one of the remote VAs to not succeed means we can respond more quickly when the 3rd VA is slow. We can respond appropriately when the 3rd VA fails or has an outage of some sort, and accommodate a small number of inconsistencies that might arise. And so that's the quorum policy that's in place now. So in doing this deployment with Let's Encrypt did a number of things to phase this feature into their production system gradually, because they're really making changes to a live operational system to put this security defense in. So first they did a staging deployment where they did internal testing of this feature on a non-production copy of the system that they use in practice. This allowed the software to be developed and tested. Then there was testing in the production environment, but without actually affecting how certificates are granted. In other words, the remote VAs were doing domain validation and logging their results, but the primary VA was driving all decisions about validation requests and the granting of certificates. So the remote VAs were just being tested out, taken through their paces, if you will. In that process, we found a number of domains that sometimes had problems, legitimate domains that sometimes had problems. And so in the initial production deployment, there was an exception list where domains with known problems working with the remote VAs were left out of doing remote multiple vantage point validation, particularly to make sure that when those domains renewed their already existing certificates, that those wouldn't be erroneously rejected. And this was possible because those domains already had certificates, and we were able, through the logging done in stage 2, to determine that they might be at risk of having a problem. This was done only for domains where Let's Encrypt had contact information to reach out to those domains and could work with them to understand and fix whatever problems were causing multi-vantage point validation to fail. And then finally, full production deployment is in process now, where all certificate requests, around 1.5 million per day, are validated by the multiple vantage points. So this gradual process let us get a lot of valuable lessons along the way, while balancing the trade-off between security and avoiding false positives with benign sites. So I want to just touch on a couple of anecdotes about our experiences working with Let's Encrypt and some interesting results. So first, we found one concern we had at the beginning was that validation would be slow and would cause certificates to be issued more slowly. But in practice, we found the remote vantage points actually typically had lower latency than the primary vantage point, because the Amazon data centers are performant and centrally located. And so in practice, we didn't find the addition of remote VAs to inflate latency. Likewise, validation bandwidth was not all that high. It's really a relatively small amount of work to coordinate the multiple VAs and to have them do a small web request to the domain. So we're using up about 0.5 megabit per second per remote VA to keep up with about 20 certificates per second. And then we saw very few benign failures. The case where the primary VA succeeds, but any remote VA fails, and remember, we can tolerate one remote VA failing without declining the certificate, happened just over 1% of the validations. And so common cases here are kind of interesting. The most common reason this happened related to DNS, where one of the remote VAs could not correctly do a DNS resolution of the domain's name. And the reason for this is interesting. What happens is someone creates a website, they go to get a domain name and DNS service, and they go and get a certificate for their site, often roughly at the same time. And so the DNS zone transfer is taking place in the background to replicate that DNS data, were sometimes not populated across the globe by the time they made their request for their certificate signing. And so we sometimes see one remote vantage point fail in its DNS resolution because the information about that domain had not yet propagated to that part of the internet. As you might expect, requests like that will often be successful upon retry. And second, we found a few cases where the domain validation requests from the multiple vantage points triggered DDoS detection in the victim network. So ironically, our attempts to be more secure in issuing certificates sometimes triggered other security systems in the victim domain. And of course, this is a reason why it's helpful not to have too many VAs. You would think more vantage points would be better, but in practice, that might not be true, because not only would more vantage points lead to higher latency and higher bandwidth, but might occasionally set off DDoS detection as well. But in practice, many of the failed validation requests were successful upon retry or by working with the particular domain to address the problem. So we wanted to quantify the security improvement. Everything I've said so far is focused on normal requests that are not attacks. So how successful is multi-domain, multi-vantage point verification in protecting against the attacks we were concerned about? So we went back to the peering testbed to launch the same kind of ethical attacks we had announced earlier when we were first identifying this attack. And we found that the Let's Encrypt quorum policy caught most of these attacks, although in some cases, a very well-connected adversary could be successful in still getting all of the vantage points to actually go to the wrong place. And second, we did a bunch of BGP simulation experiments to be able to model adversaries located not just at the locations of Columbia's peering testbed, but at randomly chosen ASs throughout the internet to understand how a randomly chosen adversary's location might affect attacks. Here we had to go a little further than existing work on BGP simulation because we can't model connectivity just at the autonomous system level. We needed to capture the unique connectivity at each AWS data center. If we treated AWS as one node in the graph, we might erroneously think all the AWS data centers would pick the same route. But in practice, that's not the case. They have a different set of peers and make independent routing decisions. So we had to extend our model of AS connectivity to capture the richness and diversity of the AWS data center BGP ecosystem. And then from those experiments, we found that the median domain is resilient to attacks from more than 90% of locations on the internet. So both of these results are positive. We can catch the vast majority of attacks using the multi-vantage point, but a well-connected adversary still has some power. And so we did some experiments of what would happen if Let's Encrypt were to add additional AWS data centers to its multiple vantage points. And we found if they would add one or maybe two more, Paris and Singapore in particular, to add a little more geographic diversity, or to have a stricter quorum policy, would go a long way towards defending against even the most richly connected adversaries. But note again, an adversary that announces a hijack that aggressively that all the vantage points in Let's Encrypt were to see the bogus route would also be quite visible in BGP monitoring systems as well. So there's a tension here where the adversary wants to be stealthy to not be detected and yet needs to fool a large number of vantage points to get its job done. It's fundamentally hard to be stealthy and have that broad a scope for an attack at the same time. In the attacks I've talked about so far, the adversary does a same prefix attack. It attacks the same prefix that the legitimate owner of the address block is using. Adversaries can do more powerful things, such as announcing smaller address blocks, where it may in fact get the entire internet to route to it rather than to the legitimate destination. Multi-vantage point verification is only so useful in this case because all of the vantage points would route to the adversary. But in practice, this we think is a less likely attack because, first of all, for a bunch of prefixes, this isn't possible. In particular, if the original prefix is already a /24, the adversary typically can't announce a yet smaller prefix without it being filtered. And again, these smaller prefix attacks that are widely distributed would be visible in BGP monitoring. And potentially if RPKI is more widely deployed in RPKI as well. So this is an important category of attack as well, but we think in practice it's hard to do these in a stealthy way. Finally, to close, I'll just mention another class of attacks that is relevant to other applications that I'll talk about in a moment, which are BGP interception attacks. And so in BGP interception attacks, the adversary's goal is not to black hole or impersonate the legitimate owner, but to just have the traffic pass through that AS en route to the legitimate destination. So in particular here, an adversary in Autonomous System 3 may want traffic going to Autonomous System 6 to go through it en route. And so what it might do is through different routers connected to different neighbors, announce different routes. In particular, it might tell Autonomous System 7 that it has a very attractive route to the destination, so that Autonomous System 7 will route through 3, while simultaneously having AS3 retain its own route through Autonomous System 4. As a result, 7 will route through 3's route, but 3 will forward that traffic onward to the legitimate destination. And this allows an adversary now to do eavesdropping on traffic as it goes through the internet. And we've seen in other applications we've studied this to be a very effective attack for particularly attacking anonymity systems like Tor. So just stepping back, there are a lot of applications on the internet that have security and privacy concerns beyond certificate authorities. Some of them use domain validation, much like certificate authorities do. Some websites, if you change your account password, will do domain validation. If you are restaurant review or hotel review sites will sometimes require the owner of a hotel or restaurant to validate that it controls the restaurant or hotel's website before allowing it to update other information at the review site and so on. So domain validation is actually more widely used than just for CAs. And as I mentioned, anonymous communication like Tor relies on the underlying routing system to deliver traffic with the assumption that the paths to the internet are independent. An adversary that can launch BGP interception attacks can put itself on the path between the client and Tor and between Tor and the server that the client is speaking with. By so doing, adversaries can do traffic analysis attacks that can break the privacy and anonymity that Tor is trying to provide. And here too, we've launched ethical hijacks and ethical interception attacks to demonstrate that Tor's anonymity properties can be compromised by network layer attacks. And finally, as I mentioned earlier in the talk, others have demonstrated that BGP can be used to attack Bitcoin by disrupting the consensus protocol that's run among the nodes in the Bitcoin network. So all of this points to the fact that cross-layer attacks are a serious problem. Assumptions in one layer can be violated by the layer below, leaving the adversary a lot of opportunity to work across layer boundaries to do attacks that application developers and network protocol designers might both be ignoring. Fortunately, that means we can use application layer defenses that are often easier to deploy because they don't require global agreement to deploy. But to be clear, I don't think that means we should abandon the important work that's taking place on network layer defenses, such as RPKI and manners and more, because ultimately it's costly for every application to have to develop its own defenses, and a single solution that protects the network layer will protect a lot of applications, not just these large applications that are particularly strong in having security and privacy concerns. And so a way forward is to, in the meantime, protect these popular and important applications and important prefixes that these applications use, while we continue the important work of securing the routing system. And hopefully also find ways to incentivize greater deployment of these BGP security solutions, both by raising awareness of the severity of these application level attacks, and perhaps in using routing solutions that favor networks that have gone a part of the way towards their role in making the internet routing system more secure. So thank you. I'd be happy to take questions. I also here point to some papers that go into more detail about the studies we've done. Happy to take your questions.
Hello, everyone. We'll continue next with Q&A. Dr. Rexford, please expand on the topic of hijacking an authoritative DNS server instead of a website.
Right. So in the attacks I mentioned in the talk, the adversary is attacking a domain validation request done over HTTP to the website, where the domain owner is expected to put up content at a particular URL. But there are other ways to do that could be done via email servers or via DNS servers. So for example, the certificate authority could require a particular TXT record to be placed at the site's authoritative DNS server. And a similar attack would work there as well, where the adversary would hijack the address block of the authoritative DNS server at the time of the domain validation request in order to return the expected answer via DNS. Now, something like DNSSEC were in place, that wouldn't necessarily be a problem, but it isn't widely enough deployed to prevent that kind of attack. And similarly with email, you could imagine intercepting the email traffic in order to be able to answer the email appropriately that the domain controls.
Okay, very good. Thank you. Another question that came up was the case of subprefix hijack with bad poisoning to evade PGP monitoring systems.
Right, that's a great question. So subprefix attack is harder for us because it could fool multiple vantage points into going to the wrong destination. And with path poisoning, it could be sculpted in such a way that only some parts of the internet would see the bogus route. So here, the main reason we're hopefully okay in this case, although there's certainly more to study here, is to fool enough of the vantage points to get the multi-quorum policy to vote that the adversary's destination is legitimate. The scope of that path poisoning can't be too narrow, because you need to pull multiple vantage points into actually routing to the wrong place. So there we're really relying on the fact that that subprefix hijack would be visible in BGP and look erroneous because it's never advertised normally. That address block doesn't exist normally in the routing system. So the combination of the need to fool a lot of adversaries and the subprefix being unusual in the first place is likely to set off some sort of anomaly detection of reasonable scope. But it's certainly something we need to study more carefully. And in particular, we're thinking about ways where the vantage points themselves might do BGP monitoring, since they're the ones most likely to see the erroneous subprefix route, precisely because they're the ones who need to be fooled into using it.
Very good. Is there anything else you would like to add to your talk? Anything else?
Yeah, I mean, first of all, my hope is that more certificate authorities adopt these defenses, because although it's great that Let's Encrypt has, and it's been really fantastic working with them, this whole attack is the defenses are only as strong as the weakest link. And so someone can go to a different certificate authority other than Let's Encrypt and potentially attack those certificate authorities. So really getting broad deployment of defenses, whether based on BGP monitoring or based on data plane validation like we've done here, I think it's necessary. Otherwise, adversaries will just go to whichever certificate authority they're able to most easily attack. Of course, Let's Encrypt is the most popular one, so it's important that it's defended against, but it's not sufficient in its own right.
Thank you. Another question came up is, speaking of DNS hijacks, what additional levels of security would DNSSEC add to protect DNS and services?
Right. So here, particularly for the attacks we're worried about, DNSSEC would prevent the domain validation attack going through DNS, because the adversary wouldn't be able to generate the appropriate signature on the DNS responses. So I think that DNSSEC deployment would help a great deal in concert with DNS-based domain validation. So that's certainly a help. Also note that if DNS-based domain validation is done, it helps with one of the issues that came up in our deployment, which is that sometimes a domain would go to Let's Encrypt before their DNS information had even fully propagated. And that caused confusion where the vantage points would sometimes be unable to do their own DNS resolution. And so in some sense, if you could get your DNS ducks in order first as a domain owner before you go and start getting ready to do HTTPS, that would have advantages as well. And finally, DNS has ways to require that only certain certificate authorities be viewed as authorized to respond on behalf of your certificates. And so that can also provide an additional way for sites to protect themselves so that adversaries wouldn't be able to go after these weaker certificate authorities and request certificates on their behalf. So I think there's a lot that can be done in using DNS to help improve the defenses against these kinds of attacks. And of course, securing DNS is important in its own right as well.
Okay, very good. You touched briefly on RPKI. Do you believe RPKI is something that will help solve a lot of those problems we're seeing with hijacks?
Yeah, I think it's very important. It's just the incremental deployment makes it tricky to defend against a strategic adversary. So it certainly goes after incrementally more sophisticated attacks as it gets more widely deployed and more widely used, and that's clearly important. So I sort of view the work in this talk in two ways. One is to say, hey, there are attacks RPKI can't fully defend against today because its full vision hasn't been yet realized, and we should make sure to defend against those attacks in the meantime. But it's really inefficient for every service on the internet to have to go through the exercise of doing application-specific defenses. It's worth it for Tor, it's worth it for certificate authorities, maybe it's worth it for blockchain too, but ultimately it'd be better if the routing system itself made these attacks much more difficult to do. So I don't see the two things in conflict. I mean, it's sort of, this is a way to limp along while we get BGP security to be more widely deployed and more sophisticated in the attacks it can defend against. And yet I hope it also raises awareness about the need to do that, actually, because of the fact that these important applications can't make reasonable assumptions about the layer beneath them without better BGP security.
Okay, well, very good. Dr. Rexford, thank you very much for joining us today.